Welcome to this first session, which is going to be looking at an introduction to statistics. Now, these slides were made entirely using R, and you can access the slides and all the content related to this lecture and the lecture on an introduction to R via the GitHub repository that will be shared at the end of this course. So, what we're going to cover in this introduction to statistics then. Well, for the learning outcomes that I want you to understand at the end of this session is to understand how we quantify differences and associations between groups of data. Because at the heart of it, this is what we're meant to be doing when we're doing research. So if you're conducting a research study and you want to know basically on any differences between certain groups, then you have to be able to quantify what those differences are, or maybe any associations between one group and another outcome. As well, we're going to look at how we draw samples of data from a larger population. Now, this is a really important consideration when understanding how statistics works, because you need to be able to understand that your sample might not be entirely representative of the population from which it is drawn. So because of this, we need to use induction to infer any differences between the samples of data that we have and seeing whether this scales up to the wider population from which we want to make inferences about. As well, to do this, we're going to look at the logic behind hypothesis testing and p-values. So this is kind of like the standard approach to statistics, typically used in research. And generally, it's just the idea that we want to see whether or not we can observe that there's a big enough difference or association in the groups of data that we're looking at to reject the idea that there's no real difference out there in the population. So it's about almost setting up this stringent test by which we say, well, for us to consider this to be a reliable difference, we have to see a big enough effect. Okay. Now, to do this, we're going to be looking at the basics of linear regression using the general linear model. Now, the reason I'm focusing on the general linear model here is that if you try and look up the number of frequentist test statistics out there that you can use, there's almost like an unlimited number that you can look at. So it can often be very easy to get lost in which analysis type you need for the certain design of your study that you're looking at. But importantly, almost all of these tests that you look at are based upon the general linear model. So understanding how to use this model allows you to almost model any sort of data that you have. Now, it might not be as robust as certain other specialist tests in certain cases, but it allows you to have this good starting off point about how pretty much any statistical engine is going to work. Okay. Now, we're going to be looking as well at not only quantifying whether or not we have the presence of an effect, but just our uncertainty in how big that effect is as well. So, of course, if we're going to be estimating whether or not there's some effect in a sample that scales up to a population, we need to understand that because our sample might not be entirely representative of the population, we should have some uncertainty there. And this is where confidence intervals come into play. So these almost describe an upper and lower bound for the effects that we have that we're trying to estimate using our linear models. Now, finally, of course, if you're going to be fitting a linear model to try and draw inferences about your sample, which scale up to the population, then we need to be able to check that our model has been fitted correctly. So are there any issues with our data which might lead to us making less than reliable inferences about that? Now, hopefully all of this should become a little bit more apparent once I get talking in a bit more detail about the things that we're actually looking at. But I'll just dive straight in and hopefully this should all make sense. So what is the aim of statistics then? Well, as I said at the start of this lecture, what we typically do when we conduct a study is we're going to draw a sample from a wider population. And then we want to use the details about that sample to draw inferences back again about the population. So for example, let's say that I'm interested in measuring the heights of every psychologist who's ever existed, okay? What I might do is I might take a sample of psychologists that I have access to right now. So maybe people who are based at the University of Sunderland. So I know that I can rely on them to give me measurements of their height, okay? Now, I might assume that this sample is quite representative of the population in general, in that maybe the demographic is of the similar makeup that you'd expect if you're going to be scaling up to a population here. So what I want to do when I take a sample of participants here, or study subjects, whatever you want to call them, is I want to be able to summarize the effects that I have in that sample. So I want to have an average there first off. So what's the average height? Where do pretty much most of the scores lie around? Now, of course, we know that you might calculate an average height, but crucially, maybe nobody's actually of that same height. So let's say I've made an average height where most people are around 5.5 foot tall. So I might decide then that looking at my sample, I need to see how far away people typically lie from this average height. So what I'll do is I need to calculate what's called a measure of variance or dispersion around this average score. So we know some people should fall above the mean, some people should fall below the mean. Now, generally, of course, what's quite interesting is that people will typically fall. You should get more people falling closer to the mean than very far away. It should be quite rare for people to be very, very far away from the mean. This is just a typical consideration of what we call normally distributed data, but we'll talk about that in a little bit. Now, of course, once I've described the sample in this way, I might maybe want to measure any additional characteristics. So, of course, maybe height functions as a measure of people's sex. So maybe men are typically tend to be taller than women, for example. So this might be something that I want to put into consideration in the model that I'm making. So I might come up with an average model for the height of men and the height of women who are psychologists. But of course, as well, as I said earlier, I need to have a measure of my uncertainty in the estimates here. So although I've got this measure of the average height from my sample and the variation in height in my sample as well, away from this average, I need to be able to understand or communicate to people that these might not be representative of the general population. So what I might do is I might calculate a measure of uncertainty around the average, which says, well, I think the average is around this height, but it might be something a little bit above this or a little bit below this when I look at the general population. So assuming I could actually measure everybody out there. I'm going to do the same thing with variance as well, so I maybe want to look at uncertainty in the estimates there. Now, what I might want to do, let's say I've measured men and women in the heights, I might then compare the samples, and I might want to look at, well, are there any differences in the average heights between men and women overall? So I might calculate a measure of the magnitude of the differences here, and the uncertainty in my estimate of the differences as well. So it's all about trying to be able to pin down what is our best estimate or our best guess for these things that we're measuring, but how uncertain am I in how well I've measured those things. Now, of course, the important thing though is that you don't need statistics unless if you're going to be measuring your entire population. So that's only going to be there if you're going to, you only really need statistics to quantify any differences between samples if you don't have access to the entire population. It's all about seeing whether or not your effects here are reliable. Now, the way in which we're going to summarize any effects or any differences that we have in our sample is going to be using descriptive statistics, which are going to describe the effects in our sample. So what is the average? What's the variation from that? And then inferential statistics, which allow me to make a decision. So I might say, okay, given the values that I have for the average height and the variance in the height between the samples, let's make a test statistic which tells me whether or not that's a reliable difference between the groups. Now that would be me using inferential statistics, which allows me to make a decision that I think this group, on average, scores higher in terms of the height than the other group. So generally, what I mean to make out by all of this is that sample statistics that we calculate are used to estimate the population that we actually care about, which might be everybody out there, all men and women, for example. So as I said in that previous slide then, the aim of stats then should be to be able to summarize, interpret and predict any complex relationships that we have based on the samples that we have at hand. Now, this can be descriptive in that I want a measure of central tendency for the sample that I have. So what's the mean or the median or even the mode of the heights that I'm looking at, for example. As well, I might want to look at any measures of dispersion, which I mentioned. So these would be the spreading scores. So this could be a range. So what's the upper and the lower limits of the scores that people have? Or what's the variance or standard deviation, which are just ways for us to kind of quantify how far people can fall from these scores based on what we know about the sample that we have. Or it can be inferential, as I mentioned earlier, where we're looking at whether or not the effects scale up to the population. Now, you might come across this if you're doing any research online yourself about people mention the difference between parametric and non-parametric test statistics. So the way that you can test for any differences between groups using inferential statistics can be using any sort of model. Now, this model can be parametric if you're trying to be describing or estimating some parameters or some variable which is out there in the population. So an example of a parameter here might be the height that I'm trying to measure from people. Now, when I estimate this from my sample, that should tell me something about how well I can kind of draw inferences about that parameter in the general population. So I'm directly trying to measure the same parameter that I'm trying to make inferences about. That would be a parametric test. However, though, what sometimes happens is that when we try to fit data using a parametric test, these tests tend to make certain assumptions about the data that we have. So what this means is that if those assumptions aren't met, so for example that the data are distributed in a certain way and they actually end up being quite skewed, this can mean that our estimates can be quite inaccurate. So in this case, when we know that, for example, we might be violating some of the assumptions of a test, we might instead use a non-parametric version of this test. Now, what happens with these non-parametric tests is instead of directly measuring, for example, height, we might say rank order the heights in the sample that we have. And then we might see basically on any differences in the ranks between samples that we're looking at. So maybe more people with the higher ranks, so the tallest heights, are associated with being men than with women. Now, what this means is that we're measuring almost some abstraction away from the parameter that we're caring about. Now, this just means that we don't have to make the same assumptions in our test. So a non-parametric test is very useful here if you've violated any assumptions of the data. But the problem with these sorts of tests is that often they can be a little bit less powerful in detecting any differences that we care about. So generally what we aim to do is run a parametric test if we can, because it tends to be the best estimate of that thing that we're trying to directly measure. So that's the kind of whole aim of statistics then, is we're going to be looking at trying to draw samples from a larger population to then make inferences about that population, largely because we just don't have access to all of the data that we could possibly collect. Now, if we did have the data from the entire population, then we wouldn't need any inferential statistics, which tells us whether or not there is maybe a difference between the groups that we're comparing. So these might be, as I said, only used for example, we're only going to use inferential statistics when we only have a smaller subset of the data that we care about. So let's say that I want to estimate the heights of astronauts. Well, there's only a handful of astronauts on the planet. So I might actually be able to get measurements for every astronaut out there. I'm sure that's probably available online somewhere as well. So if I do this, all I need to do to describe differences between maybe male astronauts and female astronauts in terms of their heights is to just look at the means. Is this mean bigger than that mean? That's all I need to do. But if I'm looking at just generally all men and all women, or maybe psychologists, when I can't measure all psychologists because maybe that data isn't out there, then what I might have to do then is make an estimate of those heights between the groups, and then use my inferential statistics to see whether the sample differences that I've observed would scale up to the general population. So as I've said, there's many different ways of conducting these stats, but we're going to focus on the general linear model using a frequentist approach to statistics. Now this is important, and I'll get into the details between maybe some different approaches to statistics as we progress. But first off, we're going to look at summarizing our data. So we've got a sample of data, we need to be able to summarize it. Now, of course, the reason we do this is you don't want to just give somebody raw data, because it's very hard for anybody to estimate just what it is when we're trying to kind of average across all of our data. So describing a summary of our data just makes it easier for you to communicate any patterns in the data that you have. It's just a way of almost like downsampling your data from what you initially had. Now there's many different types of data that we can collect, and this importantly affects the way in which we can summarize this data. So for example, data could be categorical or nominal, where essentially what these data correspond to is just categories out there. So let's say I've collected some heights for people and I want to maybe note down that they're male or female. Or they could be non-binary, or we could have other categories there as well. Now, what I might do then is I might want to model this difference in some sort of general linear model. Now, the problem with this, with me using maybe the labels of female, male, or non-binary or anything like this, is that these strings can't be processed by a linear model. So I have to assign numbers to them, which would then allow me to look at differences between the values here, between the conditions. Now, what I might do then is instead I might assign, well, maybe 1 is female, 2 is male, 3 is non-binary, and just progress like this. Or I might record some things such as like the conditions that people are in. So maybe I'm doing an experiment where I'm looking at seeing whether there's an effect of my drug versus a placebo. So I might assign people the level of 1 or 2, just corresponding to which category they belong to. Now, what's important here is that the assignments of the numbers are arbitrary. They're just, we know what they mean to us, but it wouldn't matter if I switched them around. So if 2 became female, 1 became male, or even non-binary became 1, and we shuffled all these numbers around, it doesn't really matter in terms of the interpretation of the statistics that we get to. These things are just numbers related to categories that we've assigned. But differently from this, we might actually collect some data where the numbers kind of represent a category along an ordered set. So what I mean by this is I might be looking at, for example, the place in which people finished in a race. So you might come first, second, third, fourth, fifth, or however many down the list, depending on how long the race is and how many people are in it. Now, the important thing about this is that while the differences between numbers do make sense, they do carry some sort of information, the distances between these numbers might not be the same. Okay, so what I mean by this is that, for example, somebody finished first, somebody finished second, somebody finished third, but it could be that it was like a photo finish for 1 and 2. So the actual, how closely 1 and 2 are in terms of their race times is very close together. But the third person might have lagged behind quite a way and just managed to scrape third here. So what this would mean is that while the distance between each number is just 1, so going from 1 to 2 to 3, that real world difference between these numbers is very different. So you need to be careful when you're modeling ordinal data in this way, because you might accidentally make the assumption that the differences between these numbers is indicative of basically how people have performed in the race, instead of just kind of summarizing it down to finishing order. Now, finally, what we get and what we typically tend to try to model when we do experiments is scale type data. So these are where numbers are used to represent an interval or a ratio, it should be here. So essentially what this means is that the differences between numbers is both informative and equivalent. So you could get a measure of, say, time here. So let's say I'm measuring people's race time. That would mean that maybe every second faster by each person means the same thing regardless of whether they finish first or last. A second is a standard unit of measurement here. The same thing can be said for if we're looking at lengths. So if I'm measuring heights in this sense, a centimetre is a centimetre regardless of whether you're 6 foot or 7 foot or 8 foot. If I'm looking at a centimetre difference between people, it is what it is. The same can be said for accuracy. Now, I'm going to focus primarily on categorize and summarize and scale data here, because that might be the type of data that you'll most likely come across. But what we're going to also introduce is modeling any differences between categories on a scale outcome. So it's important to be aware that generally when we look at trying to model data, what we might have is a number of predictor variables or types of data which are used to predict or make an inference about one outcome that we care about. So here my predictor might be the category that people belong to in terms of their sex, and the outcome would be the scale, as in the height that they have. So you imagine that the sex that somebody is should give me some indication of how I can predict how tall they would be. Now we have descriptive statistics, as I mentioned earlier, which is going to be there for us to just describe the pattern of effects in the sample that I have. So what we typically do here is we use a measure of central tendency and a measure of the spread of scores in our data set. So this is just a quick summary, so we don't need to look at all of our raw data. So for example, when I talk about the sample that I have, it's always informative for me to report some counts of the data that I have. So how many observations do I have? Maybe how many people took part in my experiment? Did I have to remove anybody for violating the research protocol or anything like that? So it's always useful in your reports to be discussing what is the data that you had, or what was the data that you started with, and then how much data did you have to remove prior to conducting your analyses. Now we then have a measure of central tendency. So here it might be something like the mean. So we might look at the total number of scores divided by the total number of observations. Or it could be the median, which is just the midpoint of scores that we have, or even the mode, which is the most common value that we have. So these are regular measures of central tendency. Now, when we have scaled data that we can model using a parametric analysis, typically we'll use the mean because this tends to be most informative for people. It makes a lot of intuitive sense. Now, on top of this, we might look at the dispersion or the spread of scores. So some ways we can look at this is using an interquartile range, which is basically looking at where's the middle 50% of scores that lie along a certain range, or the standard deviation, which is often used. So essentially the standard deviation here is used as a way for us to describe where the majority of our data lie on a standard scale. So let's say I have a mean height of, let's say, even if it's 5.5 foot tall, then I might describe the variation from that in terms of standard deviations away from the mean. Now, what I mean by this is we know that if the data are what we call normally distributed, which we'll touch on in just a little bit, then one standard deviation away from this mean indicates where 68% of the scores lie. Two standard deviations of the mean is where around 95% of the scores lie, while 3 standard deviations of the mean is where around 99.7% of the scores lie, so pretty much all of them. Now what this means is that across many different measurements, if we have an understanding of what the standard deviation means, it can tell us quite a lot of information about our sample. So if I know the average height, and I know the standard deviation of the height, which might be, I don't know, let's say 6 inches or something like that, then I know my average height plus 6 inches and minus 6 inches is where 68% of the scores lie, because that's one standard deviation away from the mean. If I look at the average height plus 12 inches and minus 12 inches, that's where 95% of the scores lie. So whenever if somebody reports a standard deviation and an average for any score that they're looking at, then you know that you can work out where pretty much most of those scores lie away from the average. So using these two numbers, you can quite neatly summarize almost everything you need to know about your data. Now then, how do we summarize this type of data? Well, we can summarize categorical or nominal data essentially just using a bar chart. So the nice thing about a bar chart is it visually depicts counts really well. So you can see here that I've got groups of users, and people may be using a Linux, Mac or Windows operating systems. And we're just looking at, well, how many people from my questionnaire that I've sent out have reported using these different types of operating systems. Now, very clearly here, you can see visually what the pattern is of the data. Now, this makes a lot of sense when we're just counting things up, because if people belong to this group, so you belong to Linux or you belong to Mac or Windows as your operating system, all I can really report there is the count, so how many people fell into each group here. Now, it doesn't make sense for me to calculate a mean count because it is just what it is. It's just a count of where people belong by a certain group. So let's say I assigned the numbers 1, 2, and 3 to Linux, Mac, and Windows. If I try and work out an average of these categories, it wouldn't even tell me anything. So what's 2.5 even represent here? So when it comes to categorical or nominal data, just report what the counts are. So it's really simple. If I had ordinal data instead, This can be a bit problematic for me to summarize using the mean and standard deviation, because that generally makes some assumptions about the distribution of the data that aren't being met when I have skewed data. So what I mean by skewed data is, let's say I've got maybe a bounded scale. So I may be looking at how much people kind of like or are satisfied with the statistics tools that they're looking at. So here on the plot, I'm looking at R versus SPSS. And how satisfied are you? Now, I might use a measurement scale for this, and I just ask people on a scale of 1 to 7, 1 being I hate it, 7 being I love it, how satisfied are you with your software package that you're using for doing your stats? Now, of course, this is a bounded scale. You can only score at a lower end 1, and you can only score at a higher end 7. So what this means is that, what if everybody absolutely loves R, or most people absolutely love using R, then most of those scores are going to be grouped quite heavily towards 7, and you should get very few scores towards the other end. And the same thing might happen with SPSS, though. It could be the other way. So what we might find is that you might, instead of having most of the scores being around one central value and spread out quite evenly, they might be bunched up towards one side of that value. So you might have a median score and most of the scores are above that in a certain sense, like quite closely, while below that they're spread out very far. So there's a handful of users, let's say, who are outliers and that absolutely hate using R. Okay, so the way that we can best summarize this data would be using the median, which is just looking at what's kind of the average along the middle of all the scores. And I'll use the interquartile range here, which tells me where approximately 50% of the scores lie. Now, a nice way to do this visually is using a box plot. So with this box plot, as you can see here, you've got black lines in the middle. That represents the median. So that's where the average scores lie. While the white sections of the box indicate that interquartile range where 50% of the scores lie. So straight away right here, we've got a measure of central tendency and a measure of dispersion. Now, we've also noticed that we've got some whiskers on the plot here, which is showing us essentially where 1.5 times the interquartile range, so how big that bound is, where scores 1.5 times the interquartile range lie. So this is effectively most of the rest of the scores. Now, we have dots in box plots which represent plus or minus 3 times the interquartile range, which tends to be representative of what we call an outlier. So anybody who scores here tends to be really quite far away from the average sorts of responses, which might indicate that they've done something strange, or it could just be a part of the data. It might just be that for some reason these people just really hate using R in this case. Now finally, we've got scale data. Now these are probably summarized in the way that you'll be quite used to seeing, again using a box plot. Now there are better ways to really describe this sort of data, but this is the most common way. And what we'll find is that scale data are generally summarized using the mean, along with a measure of central of dispersion, which would be the standard deviation. Now what's interesting here is that if we do have normally distributed data, you can actually interchangeably use the mean, the median, and the mode. Now again, this will make sense once you return to these slides later on, once I've described distributions of data. Now, dispersion is represented using the standard deviation here, or you can use the standard error, but I don't really want to bring in too many different terms. Or even some will talk about the confidence intervals that we'll kind of bring into play a little bit later on. But generally what you want here is just some measure of the mean and some measure of variance in the scores. Now what's interesting is that if you have small standard deviations around your mean, this indicates that most scores lie close to the mean. And if you have very large standard deviations, and in this case it would be very large error bars, which you'd see at the top of these bar charts here, the kind of bounded out black sections, these are indicative, if these are very large, of having very many scores far away from the mean. So generally, if it means that if you have large standard deviations, you don't have a lot of accuracy in trying to estimate what the true effect is, really. So then distributions of data, I've kind of alluded to this a little bit already. So this is a distribution of data in this plot, and now this distribution specifically is called the Gaussian distribution or the normal distribution. Now it's really common in sciences and in research to try and model data assuming this is the underlying distribution of the data. And that's because it is actually really pronounced in nature. This normal distribution happens quite a lot. So what do I mean by this? Well, a distribution like this is essentially used to describe how we think those samples that we've observed could have been drawn. So let's assume that I have a population, and maybe I'm looking at, again, my scores might be the differences in heights between men and women. So let's assume differences in height is something I can measure as one thing. Now, let's assume actually that there was no difference in heights between men and women overall in the population. What might happen here is that my normal distribution would be centered on 0 of no effect. That's the most likely effect out there. And it should have basically, it should be in a bell-shaped curve so that the most likely effects are either no effect or small effects, and large effects are less likely than small effects here. So when you look at this graph, what you should interpret it as is, what is the density of these scores, or how likely are these scores at certain points? So the higher the curve is, the more likely the point is when we sample from this distribution. Now, why is this really common in nature? You might be wondering, like, how do you even get a normal distribution? Why do people use this for summarizing data? Well, it's simply the case that a normal distribution tends to occur quite often when we have random measurements of things, because there's more ways to produce small differences between things than there are large differences between things. Now, one way to think about this would be, imagine I have a coin and I want to flip that coin 10 times. For me to get 10 heads out of 10, there's only one way that I can do that. I need to get 10 and then 10 and then 10 and then 10 and then 10 and on, okay? But if I want to get 5 heads out of 10 coin flips, I might produce that by getting 5 heads in a row first, then 5 tails. Or I might get 2 heads, 2 tails, 2 heads, 2 tails, and on and on. Or you can randomly shuffle these in some way, but there's so many different ways for using basically these 10 coin flips that I can produce 5 heads. So this is why this is the most common measurement for me to get if I'm looking at these 10 coin flips, essentially. Now, as I said, we use this distribution. We tend to assume that data are drawn from a distribution like this when we're modeling the data, because it's common in nature, and also because it's very easy to represent mathematically. All we need is a mean and a standard deviation to describe the normal distribution. Now, of course, it could be that data come from a distribution other than this, and if you know that, or you have some idea about this when you're trying to model your data, it's best to try and incorporate that knowledge into the model to tell it maybe that you're sampling from a different sort of distribution, but that's getting, again, a little bit advanced. So the normal distribution tends to be good in most cases. So when we know the mean standard deviation for a parameter that we're estimating, it can be accurately modeled using this normal distribution. However, when we want to estimate the mean of a sample with some unknown standard deviation out there, which is generally the case, we don't really know how far away people will fall from the mean that we're estimating, then what we use instead is called a t-distribution. So it looks a lot like that standard kind of normal distribution that we looked at just in that previous slide, except the tails are a little bit higher, they're a little bit fatter here. Now what this means is that the t-distribution almost assumes that with small samples, we're more likely to produce more extreme results. So, for example, if I'm looking at differences between groups, if I model that or draw the data from a t-distribution, I'm more likely to get big differences in heights than I am to get small differences in heights when compared to the normal distribution. But in both, no difference or small differences are more likely than big differences. Now, what's interesting with the t-distribution is that it's very good for us to try and model our data like this when we don't have a lot of data, because it changes its shape as it gets more and more data. So it tends to begin to approximate the normal distribution more and more as we get more data. So it does a good job of estimating the data that we have, but it accounts for the fact that when we have small samples, you can get extreme results just due to sampling error. So let's say, imagine I sample 2 people from a population. if I try and estimate the average height based on that, then I might have accidentally drawn two people who are very tall or two people who are very short. But instead, if I sample 2,000 people from two groups, then I might have a better estimate of what the actual average height is going to be in this way. So that's why we're trying to adjust for the fact that when you have small samples, you might get extreme results because just due to sampling error. So why do we rely on these distributions of data? You might be sitting here thinking right now, what's the point of all this? I just want to be able to summarize the data I'm looking at. Well, it's important that you know that this is an assumption of the data that you're looking at when we're trying to model it, because that's going to affect how well you can predict any results that you get from your model. So what we might generally do when we use frequentist statistics is that we're going to assume that there's no effect out there in the population. So let's say I've got men and women, I'm measuring the heights. My kind of what they call the null hypothesis is that there's no effect in the population. So there's no difference between men and women. And we want to see how likely our results would be if that were the case. So what we would do is we'll measure the heights, we'll measure the differences between these two conditions or these two groups of people. We'll see, well, assuming these data were drawn from a normal distribution, how likely are they to fall on this part of the normal distribution, or how likely are they to fall on that bit? If the difference between the heights is right towards on the tails, showing a big effect, this is probably very unlikely under that assumption that there's no effect. So we use this as a roundabout way of saying, well, if this were the case, we'd be very unlikely to observe this type of data. So because of that, we're going to take this as evidence that there is a real difference out there in the population because they're unlikely to be drawn from this distribution. Now what we generally do is we get our sample, we'll calculate some sort of statistics. So these can be called a z-score or a t-statistic. But all you need to know about these stats is that they're a standardized measure of the presence of an effect. So effectively all it is saying, well, how big is this effect? Is it big or is it small? While taking into account how big the sample is that you have and the variation in the scores that you might have in the sample. Now we can figure out how likely these scores are on that normal distribution or on that t-distribution respectively. And we see that, well, if these scores are very unlikely from these distributions, we'll take this as evidence for the presence of an effect in the population. So then to summarize this in an interim way, we can see that data can be summarized in different ways, but with scale data, we tend to summarize it with a mean and standard deviation. This is going to be what we're focusing on in the rest of this lecture. Now, many tests will rely on making assumptions about the underlying distribution of the data from which the samples were drawn. But we can use this information to be able to give us evidence in support of the conclusions that we want to make. So is there evidence that there's a true effect here in the population, or is there not, based on how likely or not our sample would be given the population that we have. Now, we'll often rely on this t-distribution because it just allows for more accurate inferences to be drawn from small samples.